Oxidation may be defined as process which involves the addition of oxygen or any other electronegative element, or as a process which involves the removal of hydrogen or any other electropositive element. Next, oxidizing agent or oxidant. An oxidizing agent or oxidant is a substance which supplies oxygen or any other electronegative element or removes hydrogen or any other electropositive element. An oxidizing agent, after carrying out oxidation, is itself reduced in a chemical reaction. Reduction. Reduction may be defined as a process which involves the addition of hydrogen or any other electropositive element or removal of oxygen or any other electronegative element. Reducing agent or reductant. A reducing agent or a reductant may be defined as a substance which supplies hydrogen or any other electropositive element or removes oxygen or any other electronegative element. A reducing agent, after carrying out reduction, is itself oxidized in a chemical reaction. Oxidation. Oxidation may be defined as a process in which an atom or ion loses one or more electrons. That is why oxidation is also called de-electronation. Reduction. Reduction may be defined as a process in which an atom or an ion gains one or more electrons. That is why reduction is also called electronation. Oxidizing agent or an oxidant, a substance, atom, ion or molecule which can readily lose electrons to other substances is called a reducing agent or reductant, while a substance, atom, ion or molecule which can readily accept electrons from other substances is called an oxidizing agent or an oxidant. Oxidation. Oxidation is a process in which one or more electrons are lost. Reduction. Reduction is a process in which one or more electrons are gained. Oxidant. Oxidant is a substance which can accept one or more electrons. Reductant. Reductant is a substance which can donate one or more electrons. Oxidation number of an element may be defined as the charge which an atom of the element has in its ion or appears to have when present in the combined state with other atoms. Oxidation numbers are also called oxidation states. Rules for assigning oxidation numbers. First rule: the oxidation number of all the atoms of different elements in their respective elementary states and allotropic forms is taken to be 0. For example, N2, Cl2, H2, He, P4, S8, O2, O3, C, diamond or graphite, Br2, Na, Fe, Ag, etc. The oxidation number of each atom is 0. Rule second: the oxidation number of a monoatomic ion is the same as the charge on it. For example, oxidation number of Na plus, Mg2 plus and Al3 plus ion are plus 1, plus 2 and plus 3 respectively, while those of Cl minus, S2 negative and N3 negative ions are minus 1, minus 2 and minus 3 respectively. Rule third: the oxidation number of hydrogen is plus 1 when combined with non-metals and is minus 1 when combined with active metals called metal hydrates such as LiH, KH, MgH2, CaH2, etc. Rule 4: the oxidation number of oxygen is minus 2 in most of its compounds except in peroxides like H2O2, BaO2, etc., where it is minus 1. Other interesting exceptions are found in the compounds OF2, oxygen difluoride, and O2F2, dioxygen difluoride, where the oxidation number of oxygen are plus 2 and plus 1 respectively. This is due to the fact that fluorine, being the most electronegative element, known as always an oxidation number of minus 1. Rule 4: the oxidation number of oxygen is minus 2 in most of its compounds except in peroxides. This is done already. Rule 5: in compounds formed by union of metals with non-metals, the metal atoms will have positive oxidation numbers and the non-metals will have negative oxidation number. For example, the oxidation number of alkali metals Li, Na, K, etc. is always plus 1, and those of alkaline earth metals Be, Mg, Ca, etc. is plus 2. B. The oxidation number of halogens FCl, Bri is always minus 1 in metal halides such as Kf, AlCl3, MgBr2, CdI2, etc. Rule 6: in compounds formed by the union of different elements, the more electronegative atom will have the negative oxidation number, whereas the less electronegative atom will have positive oxidation number. For example, N is given an oxidation number of -3 when it is bonded to less electronegative atom as an NH3, and Ni3 but is given an oxidation number of +3 when it is bonded to more electronegative atom as an NF3. Next, since fluorine is the most electronegative element known, so its oxidation number is always -1 in its compounds, that is oxides, interhalogen compounds, etc. Next, in interhalogen compounds of F, Cl, Br and I, the more electronegative of the two halogens gets the oxidation number of -1. For example, in IF7, the oxidation number of F is -1 while that of I is +7. Similarly, in BrCl3, the oxidation number of Cl is -1 while that of Br is +3. Rule 7. In neutral compounds, the sum of the oxidation numbers of all the atoms is 0. Rule 8. In complex ions, the sum of the oxidation number of all the atoms in the ion is equal to the charge on the ion. Rule 9. The polyatomic ions, the algebraic sum of the oxidation number of all the atoms in the ions is equals to the charge on the ion. For example, the sum of the oxidation number of all the 3 oxygen atoms and 1 carbon atom in the carbonate ion CO2 negative 3, CO3 2 negative is -2. A term which is more oftenly used for oxidation number is oxidation state. For example, in CO2, the oxidation state as well as the oxidation number of carbon is +4, while the oxidation state or oxidation number of oxygen is -2. This means that the oxidation number denotes the oxidation state of an element in a compound. Metals invariably have positive oxidation state while nonmetals have positive or negative oxidation states. Transition metals usually display several oxidation states. The highest positive oxidation state for S block elements is equal to its group numbers, but for P block elements it is equal to group number -10, except for noble gases. However, the highest negative oxidation state for P block elements is equal to 8 minus the number of electrons in the valence shell. In other words, the highest positive oxidation state increases across a period in the periodic table. For example, in the third period, the highest positive oxidation state number increases from +1 to +7. Group 1, element Na, compound NaCl, oxidation state of Na, element in the compound is +1. Group 2, element Mg, compound MgSO4, oxidation state of Mg element in the compound is +2. Group 13, element Al, compound AlF3, oxidation state of Al element in the compound +3. Group 14, Si element, compound SiCl4, oxidation state of Si is +4. Group 15, element P, compound PF5, P4O10, oxidation state of S of P is +5. Group 16, element S, compound SF6, SO3, oxidation state of S is +6 in both. Group 17, element Cl, compound HClO4, Cl2O7, oxidation state in both Cl is +7. Oxidation. Oxidation may be defined as a chemical change in which there occurs an increase in the oxidation number of an atom or atoms, while reduction may be defined as the chemical change in which there occurs a decrease in the oxidation number of an atom or atoms. A redox reaction may then be defined as a reaction in which the oxidation number of atoms undergoes a change. This definition in terms of oxidation number. The next, oxidizing agent or oxidant definition in terms of oxidation number. So, an oxidizing agent or an oxidant may be defined as the substance, the oxidation number of whose atom or atoms decreases, that is oxidizing agent or oxidant. Next, reducing agent or reductant may be defined as substance, the oxidation number of whose atom or atoms increases. Next is difference between valency and oxidation number. Valency. Valency is the combining capacity of an element. It is defined as the number of hydrogen atoms or double the number of oxygen atoms with which an atom of the element combines. Oxidation number. Oxidation number is the charge which an atom has or appears to have when present in the combined state. Valency. Valency is only a number. As such, it does not have plus or minus sign attached to it. For example, in H2O, the valency of oxygen is 2 and that of hydrogen is 1. Oxidation number. Since the oxidation number refers to the charge, it can be positive or negative. For example, in H2O, the oxidation number of oxygen is -2 and that of hydrogen is +1. Valency. Valency of an element cannot be 0. Oxidation number. Oxidation number of an element can be 0. For example, the oxidation number of carbon in CH2Cl2 is 0. Valency. Valency. Since atoms always combine in simple whole numbers, therefore valency of an element is always a whole number. Oxidation number. In reality, no element can have a fractional oxidation number, but if in a compound the same element exists in two different oxidation states, then its average oxidation number may have fractional value. For example, the average oxidation number of Fe in Fe3O4 is plus 8.3 and that of S in Na2S4O6 is plus 2.5. Valency. In some cases, the valency of an element is fixed in all its compounds. For example, the valency of C is 4 in all its compounds with CH4, C2S6, CH3Cl, C2H4, C2H2, CH2Cl2, CHCl3 and CCl4. Oxidation number. The oxidation number of an element may be different in different compounds. For example, the oxidation number of carbon is -4 in CH4, -3 in C2H6, -2 in CH3Cl, -1 in C2H2, 0 in CH2Cl2, +2 in CHCl3, +3 in C2Cl6 and +4 in CCl4. Valency. The valency of an element may be variable, but in variation is limited to only two values. For example, the valency of nitrogen is either 3 or 5 in all its compounds, whereas N2O, NO, N2O3, NO2, N2O5, N2, N2H2, N2H4 and NH3. Oxidation number. The oxidation number of an element may also be variable, but the variation is too large. For example, oxidation number of N is +1 in N2O, +2 in NO, +3 in N2O3, +4 in NO2, +5 in N2O5, 0 in N2, -1 in N2H2, -2 in N2H4 and -3 in NH3. Formula and chemical name of the compound: Cu2Cl2 cuprous chloride, CuCl2 cupric chloride, FeSO4 ferrous sulfate, Fe2SO4 whole thrice ferric sulfate, Cr2O3 chromium trioxide, Na2Cr4 sodium chromate, V2O5 vanadium pentoxide, K2Cr2O7 potassium dichromate, K2MnO4 potassium manganate, KMnO4 potassium permanganate, Mn2O7 manganese heptoxide. Types of redox reaction. Combination reaction. A reaction in which two atoms or molecules combine together to form a third molecule is called a combination reaction. For example, A plus B, arrow C. Decomposition reaction. A reaction in which a molecule breaks down to form two or more components is called a decomposition reaction. Displacement reaction. A reaction in which an atom or ion in a compound is replaced by an atom or ion of some other element. It is called a displacement reaction. Types of displacement reaction. Metal displacement reaction, non-metal displacement reaction. Metal displacement reaction. In this reaction, a metal in the compound is displaced by some other metal in the elemental state. Non-metal displacement reaction. In this reaction, a metal or non-metal displaces another non-metal from its compound. Salt bridge and its function. The two main functions of the salt bridge are as follows. First, it allows the movement of ions from one solution to the other without mixing of the two solutions. Thus, whereas electrons flow in the outer circuit in the wire, the inner circuit is completed by the flow of ions from one solution to the other and hence the current flows. Second, it helps to maintain the electrical neutrality of the solutions in the two half cells due to flow of ions. If the salt bridge is not employed, the flow of electric current will not occur. Question. Why does the electrochemical cell stop working after some time? The electrode. Answer. The electrode potential of any electrode depends upon the concentration of ions. With time, as the cell operates, the concentration of the metal ions in the anodic compartment increases, and hence electrode potential of anode also increases. At the same time, the concentration of metal ions decreases in the cathodic compartment, and hence electrode potential of the cathode also decreases. Ultimately, the electrode potential of the two electrodes become equal. At this stage, the cell stops working, since E cell, which is equal to the difference of the electrode potential of the cathode and anode, becomes 0, and hence electrochemical cells stop working after some time. Next question. What would happen if no salt bridge were used in the electrochemical cell? Answer. The positive ions formed by the loss of electron will accumulate around zinc electrode, and negative ions left after reduction of Cu2 plus ions will accumulate around copper electrode. Thus, the solution will develop charges and the current stops flowing. Further, since the inner circuit is not complete, therefore the current stops flowing. Features of an electrochemical cell. First, the zinc rod at which the oxidation occurs is called the anode, while the copper rod at which the reduction takes place is called the cathode. The overall reaction taking place in an electrochemical cell is due to two half reaction, one occurring in each beaker. Each beaker constitutes a half cell, also called the electrode or the redox couple. Thus, a half cell or an electrode consists of a metal rod dipped in the solution of its own ions. The reaction taking place in a half cell is called a half cell reaction. Thus, equation first and second represent two half cell reactions. The half cell reactions occur at anode is called oxidation half cell reaction, while that occurring at the cathode is called reduction half cell reaction. For example, equation first represent oxidation half cell reaction, whereas the equation second represents reduction half cell reaction. The overall redox reaction is then obtained by adding the two half cell reaction. The two half reaction always takes place simultaneously, that is, half cell reactions cannot take place independently. Since electrons are produced at the zinc electrode, this electrode is rich in electrons and pushes these electrons into the external circuit and hence acts as the negative pole or electrode. The copper electrode, on the other hand, is deficient in electrons, since it needs electrons to reduce Cu2 plus ions into Cu, and thus pulls the electrons from the external circuit. As a result, it acts as a positive pole or electrode. The electrons flow from the negative pole to the positive pole in the external circuit. However, conventionally, the current is said to flow in the opposite direction. As copper from copper sulfate solution is deposited on the copper electrode and sulfate ions migrate to the other side, the concentration of copper sulfate solution decreases as the cell operates. Consequently, the current falls with the passage of time. As a result of redox reaction, the weight of copper rod increases while that of zinc rod decreases. This gain and loss in weights of the metal rods is in the ratio of their equivalent weights. For example, loss in weight of zinc rod upon gain in weight of copper rod. Summary. Oxidation occurs at anode while reduction occurs at cathode. Anode act as the negative pole while cathode act as a positive pole. Electrons flow from anode to cathode in the external circuit while current flows from cathode to anode. Chemical energy of the redox reaction occurring in the galvanic cell is converted into electrical energy. Electrode potential. The tendency of an electrode to lose or gain electrons is called electrode potential. Since each electrode represents a half cell, therefore electrode potential is also called potential for half cell. Measurement of standard electrode potential. The absolute value of potential for a single electrode cannot be measured directly because of the following three reasons. First, a half cell reaction cannot take place independently. Second, it is relative tendency to lose or gain electrons. Third, for purpose of measurement, as soon as another metal conductor is put into the solution, it will set up its own potential. In view of these difficulties, the electrode potential has to be measured against some reference electrode. The reference electrode used is the standard or normal hydrogen electrode, NHE. It consists of a platinized platinum electrode. Platinum electrode having a coating of black platinum dipped in 1 m solution of H plus ions at 298 Kelvin, and pure hydrogen gas maintained at a pressure of 1 atmosphere is bubbled through the solution containing platinized platinum electrode. The finely divided black platinum coated over platinum absorbs H2 and thus helps to establish a rapid equilibrium between H2 and H plus ions. When in a cell, this electrode acts as an anode, that is, oxidation takes place. The following reaction occurs, that is, some hydrogen gas changes into H plus ions which go into the solution. H2 arrow 2H plus 2 electrons. When this electrode acts as the cathode, that is, reduction takes place, the following reaction occurs: 2H plus 2 electron arrow H2, that is, some H plus ions from the solution change into H2 gas. Thus, the electrode is reversible with respect to H plus ions. This electrode is usually represented as Pt, H2 bracket G, 1 atm, H plus bracket AQ aqueous, CONC equal to C. The electrode potential of the standard hydrogen electrode is taken as 0. To determine the electrode potential of any electrode, a cell is set up using this electrode as one of the electrodes, and the second electrode is the standard hydrogen electrode. The EMF of the cell is measured, as the EMF of the cell is the difference in the electrode potential of the two half cells, and since the electrode potential of the standard hydrogen electrode is taken to be 0, therefore the EMF of such a cell will directly give the electrode potential of the cell under investigation. The direction of flow of current further indicates whether oxidation or reduction takes place at the electrode under investigation with respect to the hydrogen electrode. According to the IUPAC convention, the electrode potential is given a positive sign if reduction occurs and a negative sign if oxidation occurs at the electrode under investigation with respect to the hydrogen electrode. Electromotive series. The standard electrode potential of a large number of electrodes have been determined using standard hydrogen electrode as the reference electrode, for which the electrode potential has been arbitrarily taken as 0. By convention, standard electrode potentials refer to reduction reactions. It is because of this reason that earlier they were referred to as a standard reduction electrode potential. If, however, reactions are written in the opposite way, that is, as an oxidation reaction, the electrode potential are referred to as a standard oxidation electrode potential, since reduction half reaction is just the reverse of oxidation half reaction. The oxidation potential of any electrode is obtained from the reduction potential just by changing the sign. For example, the standard reduction potential of the electrode Zn2 plus oblique Zn AQ for the reaction Zn2 plus AQ plus 2 electron arrow Zn S is 0.76 V volt. Then the standard oxidation potential of the electrode Zn oblique Zn2 plus AQ for the reaction Zn bracket S arrow Zn2 plus AQ plus 2 electron is plus 0.76 volt. According to the latest convention adopted by IUPAC, the term standard oxidation electrode potential and standard reduction electrode potential are not used, but only the term standard electrode potential is used, and the half cell reactions are always written as reduction reactions. Standard electrode potential is given a positive sign if reduction occur at that electrode WRT with respect to the standard hydrogen electrode, and is given a negative sign if oxidation occurs at that electrode. The standard hydrogen electrode, the further the magnitude of the standard electrode potential is a measure of the tendency of the half reaction to occur in the forward direction, that is, in the direction of reduction. The standard electrode potential of a number of electrodes at 1 m concentration of the dissolved ions at 298 Kelvin are given in the table. The oxidizing agents are written in decreasing order of their strength, that is, the tendency of the oxidation half reaction goes on decreasing as we move from top to bottom. Such a list of oxidizing agents arranged in a decreasing order of their strength is called the activity or electromotive or electrochemical series. Application of the electromotive series. First, to compare the relative strength of oxidizing and reducing agents. Second, comparison of reactivities of metal. Third, to predict whether a metal will liberate hydrogen from the gaseous solution of acids or not. Fourth, EMF of an electrochemical cell. So EMF of a cell may be defined as the difference in the electrode potential of the two half cells when the cell is not sending current through the circuit. E cell is equals to standard electrode potential of cathode minus standard electrode potential of anode. E cell equal to E cathode minus E anode. In order to determine the reaction taking place in the cell, the following steps are followed. Write reduction equation for both the electrodes along with their electrode potential, one after the other. Second, balance the electrical charges and the number of atoms of each element on either side of each of the above two reduction equations. Third, multiply each reduction equation by a suitable integer so that the number of electrons involved in both the half reactions are equal. It may be noted that while multiplying half reactions with suitable integers, their E values are not multiplied by any such integers because these values simply convey the tendency for reduction. Fourth, subtract the equation with lower electrode potential from one having higher electrode potential. This difference gives the EMF of the cell. The electrode with higher reduction potential has a strong tendency to gain electrons and hence act as the cathode, while the electrode with lower reduction has a strong tendency to get oxidized potential act as the anode.